All right, so let's get started with the end of chapter 13. The end of chapter 13 is not that bad. Some of these reactions we actually know how to do already. So let's review a little bit of substitution. First type of substitution reaction we covered last term was SN1. And we said with an SN1 reaction, it works with an alcohol. But what do we need in order for that OH to fall off? Yeah, we need to convert it to a good leaving group. We discussed two different ways last term of doing that. One way was tosyl chloride. You can use tosyl chloride, but we said that's normally better for SN2 reaction. What's the other method? Yeah, strong acid, right? So if we use a really strong acid like a halo acid, I'll just call this HX, we can do an SN1 reaction, and we can convert between an alcohol and a haloalkane, and we generate water as our leaving group. Remember, hydroxide on its own is a terrible leaving group. For SN2, we've got a variety of different options. The other method I heard shouted out that can convert an alcohol into a good leaving group is tosyl chloride. We'll abbreviate that TSCL. What solvent do we normally use? Pyridine, so I'll abbreviate pyridine PYR. And then in the second step, we can add in usually some sort of salt. I'll call this NaX, where X is our halogen. And by doing that, we can again convert our alcohol to a haloalkane. This method is really nice, it's gentle, it's tolerant of a wide variety of functional groups. However, we can brute force the alcohol off and use a strong acid, so I'll call this HX again. And you can actually do an SN2 reaction of a primary alcohol as well. If you want to do chlorine, there's a little bit of a hiccup, so I'm going to do an alcohol. This time we want to add on a chlorine. You actually can't use HCl directly. The activation energy is just too high. So if you do want to add in a chlorine, you do HCl and zinc 2 chloride. This allows you to add on a chlorine. Whoops. So must use catalyst with chlorine. What about fluorine? Do we ever install fluorines? What's the problem with HF? It's too weak of an acid. And carbon-fluorine bonds are really, really strong. There are other ways to install fluorines onto carbons, but for the most part, we don't observe a similar type of stereochemistry. What's one other important thing about SN2 reactions in terms of stereochemistry? Yeah, we're going to invert the stereochemistry. So if we are doing this at a stereo center, we do have to be careful. The other thing we have to be careful of is secondary alcohols. So let's say I've got this alcohol and I've got HX. What will my product be? We can protonate our alcohol, turn it into a good leaving group, but are we going to undergo SN1, SN2, or could we do a little bit of both? We might get a little bit of both. So one problem with secondary alcohols is you can get rearrangement reactions. So rearrangement can occur with secondary alcohols. It's always something you've got to watch out for. Is if a rearrangement can happen, it most likely will happen. All right, so these are all review of term 1 reactions. Let's start to delve into a little bit of new chemistry. All right, the new reactions we have are pretty straightforward and effective. We've got an alcohol. We can convert it to a chlorine by using a new reagent called thionyl chloride. So it's SOCl2 and pyridine.
That's sulfur, oxygen.
Sulfur, oxygen, and 2 chlorines. We'll go through the mechanism here in a second, but I just wanted to present the reagents. If we want to install a bromine, we use phosphorus tribromide, so PBr3. And this is a one-step route.
So this only works for primary alcohol?
For the most part, you typically see it with primary alcohols. You can see it with secondary alcohols. I believe tertiary alcohols are pretty bulky, and we'll discuss the mechanism, and it'll make more sense later. So you can use thionyl chloride, you can use HCl and zinc 2 chloride. Doesn't really matter, so you may be asking, well, why would you choose one over the other? So why might we use... So stereochemistry could be one. Another thing you have to watch out for is if you're throwing HCl into a reaction that has basic sites on there, you might do side chemistry on your basic sites. So thionyl chloride allows some unwanted side reactions to occur, same with PBr3. Once you get into more complicated intermediates, you do have to be aware of potential side reactions occurring. So let's do our mechanism for thionyl chloride. For SOCl2, and this is thionyl chloride. All right. First thing we said is with the primary alcohol, we've got a bad leaving group. It's not going to fall off very easily. And so what we use is this thionyl chloride reagent. And this is like the world's greatest electrophile. It really, really, really wants electrons. So the... What's that? Yeah, for the most part, we're going to see this reagent a few different times. If you look at the sulfur-oxygen bond, another way of thinking about this is a sulfur-oxygen single bond, where this oxygen's negative and the sulfur's positive. So that sulfur is in desperate need of electrons right now. This oxygen, because of that, will donate its lone pair into that sulfur, will kick up electrons. Oops, let me make this arrow go down bigger. And now we'll end up with our oxygen added in.
And the resonance structures, can we make that a CO instead of a carbon, please?
Oh, thank you. Good catch. So we've got 2 chlorines. We've got an oxygen with the negative charge. We've got an oxygen with a positive charge. So we've got this Witter ion intermediate. All right. Next thing we're going to do is usually a deprotonation. Yeah. So if we've got pyridine around, this pyridine is a weak non-nucleophilic base, meaning it won't do any SN2 chemistry or SN chemistry at all. It'll just grab this proton and we'll almost be there. All right, so we've got this oxygen with the negative charge. Let me move this up a bit. This oxygen with the negative charge is relatively unhappy, so it's going to clamp down. And then what do you think the next step will be? So if we move that electron down, sulfur has too many bonds. So we might want to break one of the sigma bonds. Which sigma bond do you think is going to be weakest between sulfur and something else? The chlorine. So chlorine is a really good leaving group. We remember that from SN2 chemistry. So we'll kick off this chloride. Okay, now we've created a really good leaving group.
Are we gonna have to show this?
Yep, this is a mechanism I will want you guys to know. We're actually going to use this reagent a few different times over the course of the year. All right, now the nice thing is we've ejected off a chlorine. Chlorine's a good leaving group. It's an OK nucleophile. So this chlorine will come, do a backside attack, and kick off our excellent leaving group.
Where's another chlorine group?
So this chlorine that fell off in this step is now floating around in solution, right?
Oh, okay.
So that chloride can act as a nucleophile. Okay, so we've got our chlorine installed and we've got our final product, but now let's account for our byproduct that formed. We've got this oxygen with a negative charge. Negative charge isn't too happy, so again, this negative charge will kick down and eject off a chlorine. This results in sulfur dioxide plus chloride. Oops. Come on. And sulfur dioxide is not fun to work with. Does anybody know why it's not fun to work with? It smells like you left eggs in your car on a hot summer day for about a week. Sulfur dioxide smells awful. It's actually used occasionally to disinfect products, so you may run into it in like the wine industry. They'll use sulfur dioxide to kill natural yeast. So for example, in Oregon, the yeast produces really musty smelling wine. So what they do is they kill off all the natural yeast, then they get the good yeast from France, and then they input it into their wine to prevent that musty flavor. Sulfur dioxide's incredibly foul smelling though. It was actually the Romans that discovered that sulfur dioxide could be used for disinfecting. But either way, you know this reaction's worked when the reaction becomes nice and stinky. That's a good qualitative test. All right, so that's our mechanism for converting an alcohol into a haloalkane, specifically a chlorine. Let's do the same thing for phosphorus tribromide now. So mechanism for PBr3, which is phosphorus.
This 3?
Mm-hmm. Should have been a 3. Sometimes my 3s look like 2.
Is that phosphorus?
Yeah, so did I misspell phosphorus?
Yeah.
Oh, phosphorus. This is why I don't teach English. It's for us tribromide. Here we go. Did I spell it right this time?
Yep.
All right. You guys are like my spell check. All right. Again, we've got our primary alcohol, which is a bad leaving group. So we've got to find a way to convert this into a better leaving group. This time we've got phosphorus with 3 bromines coming off. And our oxygen will attack this phosphorus and kick off a bromide. Now we've got our oxygen phosphorus bond. This bromine is not a very good base, but we'll show it doing this deprotonation step. This is more of an equilibrium reaction. Okay. And Actually, let me just change this to a generic base. So we'll have our base come and do that deprotonation, not the bromine, because we need the bromine in the second step. Once we've got that bromine on there, we've now converted this oxygen into a good leaving group. And this bromide will do an SN2 attack, kick off our good leaving group. And now we've got our desired haloalkane.
So that's a BR instead of a B, right?
Yes, that's up here we've just got a generic base. So we need a non-nucleophilic base. In order to do that deprotonation, and then our bromide that got kicked off in that first step will act as a nucleophile and kick off our good leaving group. Yep.
How do we know which one of the substitutes?
So if you're adding on a chlorine, you need to use the thionyl chloride.
Just in general, in the real world.
It really comes down to what halogen you want to install. So if you want to install a chlorine, your options are limited to thionyl chloride or hydrochloric acid and zinc chloride. But if you want to install bromine, you've got to use phosphorus tribromide. So it really just comes down to what your synthetic aim is for the reaction. All right, and then the byproduct from this reaction, is just, this should be a plus. This is just your phosphorus salt, and we're not going to be overly concerned with how that degrades. So these are really useful, and why might these be useful for a synthesis problem? Why would we ever want to convert an alcohol into a halogen? Because I asked you to on the PODs. What can we do with haloalkanes? We can make them into double bonds, so we could do elimination reactions. That could be a valuable tool. We could also do another SN2 substitution reaction and do alkylations, things like that. So this becomes really synthetically valuable as a way of interconverting between an alcohol and an alkene, or an alcohol and do an alkylation. Or we could even convert this into a Grignard reagent. We could add it into a ketone or aldehyde. Knowing how to convert things into haloalkanes is a very important synthetic step. All right, so let's briefly review elimination reactions involving alcohols. One thing I will say is if you are rusty on this stuff, please review Chapter 8, if rusty. I know it was a while ago when we covered elimination reactions, but they're not going away. First one, we can have a secondary or tertiary alcohol. And if we want to do an elimination reaction, what reagent do we need? Not a strong base. If we had a strong base, we would deprotonate our alcohol and we'd be stuck. So opposite direction. We need a strong acid. And all right, concentrated. Why do we want it concentrated and not dilute? You guys remember from the start of the term, we said if you have dilute acid, the equilibrium actually favors the starting material. You got to think about Le Chatelier's principle. You don't want water around in solution if you're trying to drive off water. So in this case, you want concentrated acid. What else helps favor elimination? Heat. So we can add heat, and we can drive this elimination reaction and get water to be removed. So we did that with our cyclohexanol lab. And then we said if we wanted to do an E2 reaction, let me actually add on another carbon there. We could do an E2 reaction, but what do we need to do to that alcohol before we do an E2 reaction? Yeah, convert it to a good leaving group. So let's maybe do that tosyl chloride and pyridine. All right, so if we do that, we convert our alcohol to a good leaving group, but we haven't done our elimination yet. What sort of base would we like for our elimination? Sure, sodium hydride. A nice non-nucleophilic base would favor that elimination. And then you would end up with OTS minus as your leaving group. So there are a variety of different ways to do this. Let's even account for a cation. And what other byproduct do we get when we use sodium hydride? H2 gas. So if the reaction's working correctly, you should see some bubbling off of H2 gas, and you'll end up with a sodium tosylate salt. All right. Now we get to go into some cool chemistry that we talked a little bit about last week in lab. Oxidation reactions. What does oxidation mean? Losing electrons. I saw some creative answers on that pre-lab quiz, so let's make sure we've got this down. So let's take this alcohol, and I've drawn in one of the hydrogens coming off of that central carbon as blue. And we said oxidation involves loss of electrons. And we said reduction is essentially the reverse of oxidation, which means it's a gain of electrons. So this would be our reduction. This would be our oxidation. And oftentimes, if we're talking about it generically, we put these in brackets. All right, if we oxidize this alcohol, what sort of functional group do you think we're going to get? Yeah, exactly. So last week in lab, we were making an aldehyde, but in this case, we would make a ketone. All right, so let's go through and determine the oxidation number for each of these. I want you to determine the oxidation number for that red carbon on the left and this red carbon on the right. You guys remember how to do that from last week? What's more electronegative, carbon or hydrogen? Carbon. So it's going to get both of these electrons, so I'll draw those in both as green dots. What's more electronegative, carbon, or is it a tie? Tie. So it gets half of this, so I'll draw in one electron for each of those. And then what's more electronegative, carbon or oxygen? Oxygen. So that carbon doesn't get any electrons from that bond. So we've got 4 green electrons that belong to that carbon. Carbon normally has a valence number of 4. So this oxygen has an oxidation number of 0. All right, let's do the same thing over here. If we look at this, carbon or oxygen, which one's more electronegative? Oxygen, and then we've got carbon and carbon. So what's the oxidation number going to be? Positive 2. So if we look at this, it makes sense, right? With the oxidation, we did a loss of 2 electrons, so we went from 0 to positive 2. With the reduction, we gained 2 electrons. We went from an oxidation number of positive 2 to an oxidation number of 0. Usually in organic chemistry, we'll see the transfer of 2 electrons. However, there are some reactions where you'll actually see single electron oxidations. They normally go through radicals, though. All right, so now let's talk about the oxidation chemistry behind these. We'll start with primary alcohols. Oop. All right, so if we've got a primary alcohol, we've got 2 hydrogens coming off, and we often refer to these as alpha hydrogens. They're alpha because they're directly attached to the carbon that the alcohol is attached to. And let's think about if we do an oxidation. What's something we could form if we oxidize this? Yeah, we could go to an aldehyde. Oop. All right, can we oxidize this anymore?
Yeah.
What could we oxidize it further to? Carboxylic acid. So let's go through and double check what's going on here by investigating our oxidation number. Oxidation number for this carbon, we've got 5 electrons on that carbon. It's valence number 4, so it'd be -1. If we look at this carbon, we've got 1, 2, 3, so it'd be +1. So we lost 2 electrons. And then over here, if we look at this carbon, we now only have 1 electron, so it would be +3. So again, we've lost 2 electrons. Another way of thinking about these oxidation reactions is every time you have a loss of 2 electrons, you're losing an alpha hydrogen, right? So if we look from the first step to our aldehyde, we lost one of our blue alpha hydrogens. And from the second step to our third step, we lost another alpha hydrogen. Can we oxidize this anymore? No, we're pretty much stuck at that point. We don't have any more alpha hydrogens to remove. We really can't oxidize carboxylic acids past that point.
Hydrogen that attached to another carbon?
Hydrogen attached to another carbon.
Yeah, the message side.
So in oxidation chemistry, we're primarily concerned with alpha hydrogens, meaning the hydrogens that are coming off of the carbon being oxidized. So in this case, we've gone from a primary alcohol to an aldehyde to a carboxylic acid. All right, now let's do the same thing for a secondary alcohol.
I have a question.
Yep.
So where do we get the oxygen to make the alcohol into carboxylic acid? Is it just from water?
So that oxygen was a part of the alcohol to begin with. The ox in brackets is just saying generic oxidation. We haven't talked about the reagents or mechanism behind this yet. So you see that how this oxygen here is remaining?
Yeah.
All we're really doing is changing the oxidation state of that carbon.
No, but in the carboxylic acid, yeah.
Oh, that comes from the reagent itself. And we haven't talked about the reagents, but we'll get there. I just wanted to introduce the concept behind oxidation chemistry first. All right? Shoot. So secondary alcohols. Come on. Here we go. So with secondary alcohols, we now only have 1 alpha hydrogen. So if we oxidize a secondary alcohol, what will we get out? Oh, that's a good question. How is this secondary? How can we tell if an alcohol is primary, secondary, or tertiary?
There's 2 carbons.
Yeah, exactly. So if we look at this central carbon where the alcohol is attached, it's attached to 2 other carbons, so it's secondary because of that. All right, if we oxidize this, what functional group are we going to make? Ketone. So if we remove that blue alpha carbon, we can make a ketone. All right, what if we oxidize this further? No reaction. You guys didn't get my trick. All right, because we don't have any blue alpha hydrogens, we can't oxidize it past a ketone, at least not easily. So using basic oxidation techniques, we can easily convert a secondary alcohol to a ketone, but we really can't go past that without using more elaborate chemistry. All right, let's do the same thing with tertiary alcohols. All right, tertiary alcohols. We've got our oxidant. Can we oxidize it? No reaction. Because there are no alpha protons. Same thing with that secondary alcohol example above. We could go to the ketone, but we couldn't go past the ketone because we didn't have any alpha protons available. So that's always something you've got to watch out for. All right, so now let's delve into the reagents. All right, your textbook, I mentioned this during lab, is a little bit out of date. The reagents that they use really aren't used by practicing chemists anymore. They're deemed to be traditional reagents by the chemistry community, and they're still shown on the ACS exam, so they're quite often seen in textbooks. Because of that, I'll introduce them to you, but just be aware, we used to have a nickname for these in grad school. We used to call them cancer dust. Because chromium compounds are oftentimes linked to cancer, they're awful for the environment. Typically, if you even try to order chromium compounds, you're ordering people at the company or school you work at will say, no, we won't allow you to purchase this. There's just too much liability associated with using chromium compounds. Why? In the 50s, people didn't really know better, and they just knew it worked, and they would use this. There's actually stories, this is going off track, but there are stories of labs where 20 years after people left the lab, everybody died of cancer. I'm not even kidding. I'll have to see if I can find it, but there was one article I read a few years ago that my friend showed me from the 1970s, where it looked just like a normal synthetic paper, and at the end it had a little note on the bottom, and it said, note. 3 of the 4 authors of this paper have since died, and it has been determined that these reagents are quite lethal if used for prolonged periods of time. So oftentimes during the cowboy days of doing chemistry, they just didn't know better, and they didn't find out until oftentimes it was too late. So chemists today don't like using this stuff. So we've got chromium-6. Chromium-6 is some nasty stuff, but it works well as an oxidant. Because if you think about the oxygens here, they each have -2, which means that chromium must be +6, right? And when you do this, you normally do this in sulfuric acid and acetone. And you make a reagent in situ. Which is chromic acid. Yep. If you see chromium-6, you probably shouldn't work in that lab. All right, the other reagent is a little bit bigger, but same principle applies. This is sodium dichromate. And again, we can convert this to chromic acid by using H2SO4 and water. So either of these reagents can be used to make chromic acid. Chromic acid is our active oxidant. And this, when it's written out, is normally written as Na2Cr2O7. And you'll see this quite often in the Klein textbook and on your sapling problems.
Could you tell me the name of the compound one more time?
Sodium dichromate. All right, so now let's take a look at some example mechanisms that utilize chromic acid. Chromic acid is a very strong oxidant, so let's take our primary alcohol, where we've got 2 alpha protons. And I'm going to use sodium dichromate. And in this case, what would you anticipate your first oxidation product to be? An aldehyde, exactly. So if you go through and you oxidize this, you would expect to get an aldehyde. However, this overshoots it. It's too hard to control. and you end up going straight to your carboxylic acid. This is very hard / impossible to isolate. Yep.
Is that Na2Cr2O7?
Yes. Sorry. 07. Na2Cr2O7. They say the longer you've been in school, the worse your handwriting gets. So.
It's really hard to isolate it. How do we know if there's something that happened in this reaction?
That's a good question. We know from monitoring the reaction that it goes through an aldehyde. It doesn't go straight to the carboxylic acid. The problem is the aldehyde's even more reactive than the primary alcohol starting material, so it will oxidize really quickly once it's formed to the carboxylic acid. We'll discuss a way to make aldehydes later, but you can't use chromic acid to make an aldehyde. So let's do the mechanism really quick.
So one would check would be using the MGBR and what?
So once you make an aldehyde, for example, you could use a Grignard and add your Grignard reagent into an aldehyde. In this case, with the primary alcohol, we make a carboxylic acid. Can we treat a carboxylic acid with a Grignard? No. So in this case, this wouldn't be synthetically useful for making an intermediate in a Grignard reaction. However, let's take a look at a different situation, and let's use a secondary alcohol. So now we've got our secondary alcohol. We've got chromic acid, which is HOCrOH with 2 double bonded oxygens. And this will react in equilibrium. Oops. To form a big chromate ester product, or intermediate, I should say. I'm not going to get overly involved in the mechanism, but you can imagine with sulfuric acid around, you can protonate one of those alcohols. They can act as a leaving group, and essentially you can replace on your alcohol with where that alcohol used to be. So this is all in equilibrium. We also have water around in equilibrium. This water can now grab this alpha proton. It can clamp down and kick off our chromium complex, or our chromate ester. All right, now when we do this, we've got a new functional group, which is a what? Ketone. Plus, we end up with our chromium leaving group, which has a negative charge, and we end up with hydronium ion. So it's a really efficient reaction. However, like we said, we avoid using chromium. If you want to read more about it, I'll update the class website with more modern techniques. There's ones called like the Swern oxidation and a few other ones that are much, much more common than these. But this is the one that's only shown in your textbook. All right, let's discuss our other oxidizing agent. I think we've got enough time to get through it. And the second oxidizing agent that's commonly used in your textbook is more gentle. And it actually used to be involved in breathalyzer tests for alcohol. And what we do is we take pyridine plus chromium 6 trioxide plus HCl. And when you mix all of these things together, you end up with this cation that's called a pyridinium ion. and a chlorochromate anion. So pyridinium, chlorochromate. Chemists don't like this alphabet soup, so we just call this PCC. PCC. Like Pierce Community College. I guess they're Pierce College now, so they can't use PCC. All right, let's take a look at when we would use PCC as opposed to chromic acid by looking at a few different examples. All right. Oops. So let's take our primary alcohol again. And this time we're going to use PCC as our oxidant. And oftentimes you'll see this in dichloromethane, so CH2Cl2. That's just our solvent. It doesn't really do anything besides hold the reaction. Come on. All right, and if this is a gentle oxidant, what do you think we're going to go to? The aldehyde. You guys saw in lab that there are more effective ways to make aldehydes that avoid the use of chromium. But the nice thing about this is that it won't do any sort of over-oxidation to our carboxylic acid. So we'll just put a big X through this. You don't over-oxidize. You can go straight from a primary alcohol to an aldehyde. All right, now let's take another example, but this time we'll use a secondary alcohol. And we'll use PCC and CH2Cl2, so that's our dichloromethane. What functional group do you think we'll get out if we're using a secondary alcohol as our starting material? Ketone. What's another way to get from a secondary alcohol to a ketone? Yeah, we could use Na2Cr2O7 and H2SO4 and water. Either method works for secondary alcohols. However, PCC is considered more of a gentle oxidant. If you do have other portions of your molecule that are sensitive to oxidation, PCC would be your preferred route. But for simple cases, it really doesn't matter.
So even excess, it won't over-oxidize it?
No, you can't really over-oxidize a ketone. You're kind of stuck at the ketone once you oxidize it to that point. All right, let's take a look at a practice problem. This could be one I could give you guys on a quiz. So I'll make it a 4-point fill in the box question. All right, let's say I use PCC and CH2Cl2. And we've got 4 points in there. Let's try to figure out how we would, or what our product would be in this case. What would this carbon turn into on the left? An aldehyde, right? Because it has 2 alpha hydrogens, but with PCC we're going to only oxidize it 2 electrons. What about this carbon over on the right? Ketone. All right, so let's fill in our box. We've got our aldehyde. And we get our ketone out as well. Let me clean this up.
Would you need to stay with PCC process, or
Yeah, let's do that. We'll write excess PCC. That's also one drawback to this reaction is I believe you have to use PCC in a stoichiometric quantity, which means you have to use a lot of PCC for this reaction to work. All right, let's take a look at one of the common uses, or former uses. Let's say we take a breathalyzer. Hopefully none of you ever have to do that.
Breathalyzer?
Oh, shoot. Oh, is that spelled right? Breathalyzer? Okay. It's close enough. All right. Let's say you've been going out on the town for a Friday night and you've had a little bit of some ethanol. And you're riding your bike and you're swerving around and you get a bike cop behind you and he says, "Hold on, buddy, you got to blow into this breathalyzer and I'm going to give you a biking under the influence ticket." When you blew into the old breathalyzers, they actually had sodium chromate in there.
Oh, wow.
You don't want to inhale, you want to exhale. And they also had acid in there. And when you did this, what do you think ethanol turned into? This is a strong oxidant. We've got a primary alcohol, carboxylic acid. Specifically, it would turn that ethanol into acetic acid. And the byproduct of this reaction is chromium-3. And this chromium-3 has this brilliant green color versus the starting material, which is orange. And they could use this color change to determine how much alcohol was in your system. You may be wondering, too, if biking under the influence is a real thing. It is. So don't get pulled over by a cop if you've been drinking and riding your bike. Or driving. That's even worse. But these were how the first breathalyzers came out, was using simple oxidation chemistry that they learned from their organic chemistry class. All right, we're going to skip over the oxidation of phenols and bioredox reactions. If you want, you can read through your textbook, but I'm not going to expect you to know those reactions on quiz or exam. All right, I'll see you guys in lab or tomorrow.